Okay, so good morning, everyone. And let's begin by looking at whether we have any questions. So okay, so you were confused with the first question. Let's take a look at the first question. Give me 1 second to write the objective. So we're going to look at the kernel and basis and image of a linear map. That's what we're going to study today. And the target space vectors are in general the vectors of the outputs. Okay, so these are the target vectors. And let's look at, you said problem, did you say problem one? Problem one. So first of all, I did comment on problem one on the on Friday. So I told you how to do it. And the first thing that you need to do is verify that these three vectors, there are three of them, are linearly independent. Okay, and first of all, you know precisely what these vectors are. So this is the vector 0, 0, 1. This is the vector negative 1, 0, 0. And this is the vector 1, 1, 0. So you need to begin by verifying that these three vectors are linearly independent. I hope you all remember how to do this. You set coefficients x, y, z, and you set a linear combination equal to 0. And then you try to verify that only x, y, and z, that x, y, and z have to be 0, right? Are we good so far? And then you just need to represent the vector 1, 1, 1 as a linear combination of these three vectors. That's all. Okay. So you will need to solve pretty much for x, y, and z. And again, we gave this last time. Of course, it's good to repeat things sometimes, but also on your side, it's also good to go to the recording because you will find information on the homework. And then there was a second question. Somebody asked about problem number 3. And you said, what was the question? You said, let me check the chat. Yeah, that was problem 1 that I just explained. Oh, no, the target space vectors are going to be R3, vectors of R3, and the basis for both the domain of definition and the target space is going to be the standard basis. Okay, that's the idea. We want to have the standard basis for both. Okay. No, I think the quiz was pretty standard, right? And I don't have it in front of me anymore. I mean, basically, you needed to find you would have got a 3x2 matrix, right? You needed to find T of 1, 0, 0 and T of 0, 0, 1, and then express them in terms of the basis. So let's say if you found, I'm not saying that it was 3, 5, but let's say if it was 3, 5, then you would have needed 3, 5 to be equal to x times, what was the first vector? I believe the first vector was 0, 1, right? And the second vector was 1, 1. So this would have led you to 3, 5 is equal to 0 x plus y. And this would have given you y comma x plus y. And this would have meant that 3 has to be equal to y, and 5 has to be equal to x plus y. You see, once you know that y is equal to 3, you get that x is equal to 2, and you're all set. Okay, so the first column, for example, would have been 2, 3. And then you would have to do it for the other two vectors, right? That was our quiz for today. So let me again go over the general picture that we're trying to paint here and understand and pretty much use it. So we're talking about vector spaces. So in a vector space, we have two operations, plus and minus. Somebody asked a question about quizzes. Again, we explained everything about how quizzes are graded on the first lecture. So please, we have addition and scalar multiplication between vectors. And they satisfy 8 different properties. And the central notion for us is the notion of a linear combination. So if somebody gives you vectors u1 up to un, if you scale each vector by a number, then and add them up, then you get a linear combination. So in simple terms, if somebody tells you I want a linear combination of the vectors 1, 0, 0, 0, and 0, 0, 1, 0, let's say, what is a linear combination of these vectors? So you can take 2 times 1, 0, 0. I'm just picking up a number randomly. There's no significance to why I'm taking 2. And it's going to be 2, 0, 5, 0. And that's it. So this is a linear combination of these two vectors, of this vector and that vector. And in general, we say that a bunch of vectors are linearly dependent if at least one of them can be written as a linear combination of the remaining ones. So for example, these two vectors are not linearly dependent because that would mean that one of them is a scalar multiple of the other. And that's not possible because they have zeros at different places. There's no way you can scale one and get the other. So these vectors are linearly independent, which is exactly what happens when two vectors are not linearly dependent. So two vectors can be either linearly dependent, linearly independent. What is a way that we said that you check linear dependence and independence? You take a combination. So you can do something like what I said, or in general, you could take a combination, a linear combination of the vectors that you want to check and set it equal to the 0 vector and try to find out whether you can find a non-zero solution. So here you would see that this pretty much ends up being this. So the only way that the linear combination of these two vectors is the 0 vector is if x is 0 and if y is 0, right? There's no other way. So this would mean again that these vectors are linearly independent. So a moment ago, when we're trying to answer a question regarding today's homework, the homework that is due today, we said that for those three vectors, for those three specific vectors that we had a moment ago, those were the vectors, we need to take a linear combination of them and check that the only way that that linear combination is 0 is if all the vectors are 0. Okay? Any question? Yes, there is a way to prove linear independence by using a matrix, but we have not seen this method yet. We're going to see it later. Yes, so you set it equal to 0 and you try to solve it. How did I get +1? I'm not sure I'm following that question for. Which problem did I get +1, 1, 0, 0? Yeah, of course you can unmute. Anytime you can always ask your question by speaking.
So on problem 1, there's I think it says t times 100, and I was wondering which coordinate that was, or if that's part of
So I'm not sure what t you mean, but t everywhere here means transposition, right? It doesn't mean any multiplication or anything like that. All
on
this...
the fourth row, and it says equal to 3.
This was about the quiz problem. Here I was discussing the quiz problem.
Okay. Yeah, I was.
Okay. My discussion of problem number 1 ended right here.
Gotcha. Okay, thank you.
Okay, sure. Thank you for asking this. Any more questions, please? So let me go back to my recap. So this is what linear dependence or independence is about. And if you happen to have vectors that generate a space and are linearly independent, we call them a basis. So basis means two things: linearly independent and generating the space. But we said that if you are in a space of known dimension, and the dimension is the number of vectors in a basis, then you can actually skip the one of the two things and just check that it satisfies one of the properties. Usually, it will be linear independent. So in most of the examples that you're going to see, if you're, for example, in R3 and you have 3 vectors, then you're going to check that they're linearly independent. If they're linearly independent, they form a basis. So you don't have to check that they generate a space. Somebody asks you, okay, so how do you, theoretically speaking, check that they generate a space? The answer would have been that you just try to see if every vector can be written as a linear combination. And that may actually have some interesting, I mean, that might be a non-trivial problem to solve, especially because you have to solve it for any vector. Again, hopefully you will never have to deal with such a problem, but if you have to deal with such a problem, then the way to do it is to actually show that each standard basis vector is a linear combination. If every standard basis vector is a linear combination, then everything is a linear combination. Okay, so then we talked about linear maps. So what is a linear map? A linear map is a function between two spaces that sends a sum of two vectors to the sum of the images and a scalar multiple of a vector to the corresponding scalar multiple of the image. And we said that pretty much if we are between two spaces, and in most cases here, let's be honest, we're not going to look at arbitrary spaces. So we're going to have something like Rn and Rm. So let's say R2 and R3. Then you can choose a basis U on R2. You can choose a basis V on R3 and consider the matrix of the linear map T with respect to U and V. What does that mean? That means that you encode everything that you need to know about this linear map in one matrix. That is formed how? you start with, let's say that, so the basis U is U1, U2, two vectors. And the basis V consists of three vectors because we are in R3. So what you do is you take T of U1 and you express it in terms of V1, V2, V3. So you have to find numbers, lambda 1, lambda 2, and lambda 3. And of course, these numbers are going to be unique. You take these numbers and you set them as a column in this matrix. And then you do the same thing for the other vector, and you have another column, and that gives you a 3x2 column, which happens to be a matrix that fully represents this map. And when we're going to talk about multiplication of matrices, you will see that there's actually a very concrete way in which this matrix represents the corresponding map. So are there, and this gives a complete summary of what we have seen so far. Are there any questions, please? Especially conceptual questions. If there's something that you want me to sort of dig into much with more detail, I will gladly do it.
Can you explain that third equation on the right? The T of U1.
Right. So you express the vector T of U1 in terms of the vectors of the basis of the target space. That's what it means. Basically, every time I'm going to talk about a basis, I'm going to put a line over it. So that's the silent convention that I'm pretty much using here. Okay. You asked me about applications of vector spaces. Vector spaces is a standard tool. We said that from day one in all sciences, right? And one of the standard applications is when you have a function, you linearize it. So you try to find a linear map, which is the closest possible to the original map. In that case, you consider it from the tangent space of the different directions at that point, and it acts like a linear map. So pretty much everything that we did in Calc 3 can be expressed using linear maps in terms of approximations. Okay. And in some sense, consider vector spaces to be a tool which is as fundamental in mathematics as is the multiplication table for elementary mathematics. So if you ask about the multiplication, it's used everywhere. And same thing for, so for example, if you go back to Calc 3, you will realize that for any function between two spaces, you can have the corresponding differential, which is the linear map that approaches your given map in the best possible way. Any more questions, please? Also, another standard application that we're going to see almost very soon is that by using the language of vector spaces and linear maps, we can understand and solve systems in a very efficient way. And of course, systems, in some sense, is the connecting link to many, many problems that we have. I'm talking about linear systems of equations. So fortunately for us, we will exclusively talk about linear systems in this course. Is there anything else that you would like me to discuss before I begin with today's lesson? Okay, then. So why don't we define two subspaces that come with every linear map? So to every linear map, we can attach two subspaces. Let's look at them very, very carefully. So let T from V1 to V2 be a linear map. Then we define the kernel of T. We're going to denote it by ker T as all U's in V1, so all U's in the domain of definition, whose image is the zero vector. Okay, so that's the kernel. So what is the kernel? The kernel consists of all vectors that go to the vector 0 in the image, through our map. And we also define the image of T. This is going to be denoted by image T as the subspace consisting of all the outputs. So V in V2, for which there exists a U in V1, such that T of U is V. So pretty much we're talking about, or I could rewrite this as all the T of U's for U in V1. Either way is fine. I think obviously this definition looks much simpler. Okay, so all the vectors that map to 0 are going to form the kernel. All the images of vectors in the target space are going to follow to form the image. So one of the standard questions that we're going to face when we look at linear maps is to find the kernel and to find the image. More precisely, so let me write this. So kernel T is a subspace of V1, and image T is a subspace of V2. So why don't we do an example? And in both cases, we will want to find a basis. This is the main way in which we're going to pass from talking about just the vector spaces Rn to also talking about their subspaces. So any questions before I do the example? Any questions before I do the example, please?
Can you explain what the image T1 says?
The simplest of the two descriptions is this one, which really tells you that they're the images of all vectors, meaning the outputs of this function. So the image consists of the outputs of this function. So you know what, if I work with the Venn diagrams, I mean, remember in high school you used to see the Venn diagrams, then the kernel would be all those vectors. So let's say this is the 0 vector in the other space. So all those vectors that map to the 0 vector. So this will be the kernel. And the image would be all the different vectors that you get on as images of vectors on the target space. So the kernel would be part of the domain of definition. The image would be part of the target space. Okay. Again, let me remind you of the notation that you see here. This backwards E means what? Do you remember what it means?
There exists.
There exists. Very good. This epsilon means belonging to. And yeah, that's all the strange notation that it's a good idea to remember here. Okay, let's do an example. And again, in the example, the best way to identify a subspace is by finding a basis. And please remember that when you find the basis of a subspace, you automatically find its dimension. So these are going to be two very interesting tasks. And as you're going to see, for very simple maps, we can do them quite easily. But for general maps, it might take a little more work. So let's do the following. So find a basis for the kernel of T from R3 to R with T of XYZ is equal to, I don't need a parenthesis because my target spaces are, this is just the real numbers, X minus Y plus 2Z. Okay, so let's say, imagine that this is your linear map. What is the kernel T? So the kernel T is going to consist of all vectors X, Y, Z, such that X minus Y plus 2Z is what? Is equal to 0. Very good. Okay, so let's try to identify those things. So you will see that finding the kernel, let's make this remark here, finding the kernel amounts to solving a homogeneous linear system of equations. And the beautiful thing about what I just said is that it works the other way around. So when somebody gives you a linear system of equations which happens to be homogeneous, you can automatically suppose that what they're trying to do is find the kernel of a map, of a linear map. So here the question is, how do we solve this? And the idea is pretty simple. Look what you do. You take this equation and you will usually find some free unknown. So if I start with X minus Y plus 2Z, don't expect to find a unique solution here. Just solve for X. X is equal to Y minus 2Z. And we're going to say that Y and Z are free unknowns. Free unknowns. This means that they can take any value you like. So this means that your typical vector, so the typical vector in the kernel of T looks like this. Free. Okay, let me do a more traditional E. It says free. Okay, so the typical vector looks like this. It looks like Y minus 2Z, Y comma Z. Okay, this is your typical vector in the kernel. And this means, now the question is, how do we get a basis? So the question that we should ask here is, how do we get a basis? And I'm going to show you something which is going to become pretty standard from now on in this course. So let me pause for a second. Let's take a breath and tell me if you have any questions before I show you how we can find the basis. How we can find the basis, which is going to be pretty much one of our main goals. Since X is supposed to be Y minus 2Z, and our kernel consists of vectors in 3 coordinates, I really replace x by y minus 2z. Okay, and I leave y and z that are the free unknowns as they are. Okay.
What do you mean by free unknowns?
Free unknowns means that they can take any value you like. So take y to be 10 and z to be 7. Take y to be 3 and z to be negative 1/2. And then x is defined in terms of those y and z. Okay, so when we say that an unknown is free, it means that it can take any value you like. You can have other unknowns that depend on this, but that one can take any value you like, which shows that you have infinitely many solutions. As you're going to see in this business, we will never have like 5 solutions or 7. We will have 0, 1, or infinitely many. And every time you have infinitely many solutions, they will be expressed in terms of free unknowns, meaning letter variables that can be given any value. Okay. The third row. The third row, do you mean this right here? That says kernel of t. That reads kernel of t. Kernel. So that's the abbreviation for kernel. Kernel of t. So this means kernel of this linear map. Okay. So here's what we do. Here's the standard method. You separate the unknowns. So you have a vector that has all the y's in it, and a vector that has all the z's in it. And then you factor out the y and the z. You will always be able to do this because they're linear. And you see what happens now. It turns out that your typical vector in the kernel is a linear combination of these 2 vectors, this vector and that vector. Okay, so in other words, every vector in the kernel is a linear combination of 1, 1, 0, and negative 2, 0, 1. So these 2 vectors generate the kernel. These 2 vectors generate, the other word for generate is what? So in this course, we will say generate or what is the other word? Great, span. Generate or span the kernel. So the kernel has an unknown dimension. So I cannot jump to the conclusion that they form a basis. So not only this is a case where not only do I have to check that they generate the space, but also that they are a linearly independent. So can anybody tell me, are these 2 vectors linearly independent? Yes, they are. Can we say why? Which is a luxury for this particular case. But let's take advantage of it. Nobody said that when something is granted to us so easily that we shouldn't take advantage of it. Exactly, there are 2 of them. You have 2 vectors. What I'm saying works just for 2 vectors, not for 3, not for 4, not for 5. There are 2 of them, and one has a 0 in a place that the other does not. So they're linearly independent. This means that, so they form a basis. And the dimension of the kernel is equal to 2. Okay? So we just found a subspace which occurs as the kernel of a linear map, and we just saw that it has dimension equal to 2. Because there are two vectors, right? The basis is formed by two vectors, right? The dimension is by definition the amount of vectors in a basis. Any more questions? Let me give you a problem for you to do yourselves now, okay? So the final answer would be that a basis for the kernel, a basis, you don't say the basis for the kernel consists of the two vectors that we just found. That's all. So everything that we wrote in the previous page is enough. Please try the following example. So find a basis for the kernel of T from R4 to R2 with T of X, Y, T of X, Y, Z, W is equal to X plus W, comma, Y minus W. Okay, give it a try. Give it a try. Try to see what are the vectors that map to 0, and see if you can find a basis for their subspace. Okay, give it a try. I'll give you a couple of minutes. Okay, let's do it together very slowly and carefully. So first of all, let's begin by writing down the kernel. What do I mean by this? The kernel, as we said, it will always be defined on the basis of a system of homogeneous linear equations. So the kernel of T will be all x, y, z's, and w's. What does it mean for T of this vector to be equal to 0? It means that the first coordinate has to be equal to 0, and the second coordinate has to be equal to 0. Do you all agree? Okay.
Can you repeat
Because
that?
if those two, the kernel consists of all vectors that map to 0. For the image of a vector to be 0, you need these two quantities to be 0, right? That's all I'm saying. Because these are the coordinates of the output. You want the output to be 0, so you want these two quantities to be 0. It's what we did in the previous problem, but with just one equation. Okay. Any questions? So we need to solve this system. Now, as we're going to see, usually when we work with such systems, we will try to solve with respect to the first unknowns. We will systematize this later. Okay, but for the moment being, allow me to solve it by writing that x is equal, sorry, the second equation is minus. So x is equal to w, and I'm sorry, x is equal to minus w, and y is equal to w. And here, w will be free, okay? Because it's on the other side. This is how you will know what is free and what is not. Whatever appears on the right-hand side will always be free, okay? And what else is free here? There's something else which is free. And z will be free. Yeah, you do have to write that it's free. Yeah, absolutely. Yeah, that's why I'm writing what you're supposed to write. And z is free, because z is nowhere to be mentioned here. So what does that mean? That means that because there is no restriction on z, that's why. I mean, the z is the freest thing in the world, if there's any such expression that I could use, exactly because you don't impose condition on it. So think of it this way. Let me put it in simple terms. X is not free. Why? Because it's expressed in terms of w. Y is not free because, again, it's expressed in terms of w. So in other words, there are conditions on x and y, but there's certainly no condition on w because it's on the second. It's on the right side, and there is no condition on z, because z does not appear at all. First of all, the quick answer is no. There's no way we solve it in one way and we have two free unknowns, and then we solve it in another way and we have three free unknowns. That's impossible. But you're right about the fact that depending on how you solve the system, you can have other free unknowns. Here, I believe that you could have had also no, w could not have been free here. I don't think that. No, x could have been free. X and z could have been free, I think. Okay, I think you could have done it a different way, but but let's do it in the most economical way. So your generic vector can be written as x is what? Is minus w. So you write everything in terms of the free unknowns. That's what you're going to do. Write your vector in the kernel in terms of the free unknowns. So minus w, and y is w, and then z has no restriction on it, and then you have w. So this is your generic vector. It's the typical vector. From this point on, it's the same process that we described before. So from this point, nothing changes. So you take this and you separate the w's from the z's. And this is w times negative 1, 1, 0 plus z times 0, 0, 1, 0. And now these two vectors, they generate the kernel, and they're linearly independent. Why? The same story as before. There are two of them, and they have, oh, I'm sorry, my first one is incorrect. This should have been N1. So they are linearly independent because they have zeros. There are two of them and have zeros in different places. So the dimension of the kernel is 2. And these two vectors form a basis. That's all. Okay, we will systematize this process even further. Even further. Questions, please. So why don't we take a few minutes? Okay, 1 second. There is a question. No, this wouldn't work. Okay, you write the expression on the basis of the typical vector. X is not part of the typical vector. And I repeat that you're not going to have 3 free unknowns here. Okay, it's not possible. So what you're suggesting is not working. Once you take the typical vector, the process is the usual. You separate the variables, and that gives you generators. The problem is, so you get a bunch of vectors that generate the subspace. The problem is to know that they're linearly independent. And in this case, that is checked because they are 2 of them and have the zeros at different places. Okay. So let's take a few minutes of a break, like what, 6 minutes? We have 2 vectors. 2 vectors, that means dimension 2. The basis has 2 vectors, that means dimension 2, right? Okay, so let's take a break for 6 minutes, and when we come back, we will continue. Okay, so welcome back from our break, and let's see if you have any questions on what we just did. I mean, this is going to be a pretty formula-like method, and there's going to be a little bit of an improvement later. Especially, you can see that I'm trying to give you a very simple linear map. The coordinates are especially simple, and they won't have always to be like that. But the pattern is going to remain the same. So you start by solving the system in terms of numbers and free unknowns. and then you find the generators, and then you try to check if the generators are linearly independent. Now, is it true that the generators are always going to be linearly independent? The answer is no. The answer is no. Okay, and these are going to be much more interesting situations, but you will see that we're going to use more tools in order to deal with those situations. Are there any questions before I proceed with the image?
So one more time. So W is free because it appears in both equations.
No, the reason that it's free here is because it appears on the right-hand side. So we have used it as a means of expressing our other unknowns. Okay.
Okay, thank you.
We will see later how to solve this in much more general cases. For the moment being, most of the examples are going to be as simple as this one. Okay. The main question here, which I'm afraid at this point it's really up to up in the air, is how do we determine what is going to be free? Because remember, somebody asked before, could we have chosen other free unknowns? And the answer was yes. But we're going to give a method pretty soon that will enable us to do this as a no-brainer, to determine what is going to be free and what is not going to be free. Okay? So right now, I just want you to focus on what the kernel is and what the general method for finding a kernel is. So let's work with an image now. So find a basis. For the image of the linear map T from R2 to R3 with T of X, Y, Z, T of X, Y, I'm sorry. The domain of definition is R2, so I cannot have X, Y, Z, is equal to 2X minus Y, X, Y. Okay. Again, I'm trying to give very simple coordinates. So obviously I could have had X and Y's in all three of them. I have great news for you here. So first of all, let's write down the image as a subspace. So the image of this simply consists of all the outputs. So it consists of all vectors that look like this, where X and Y can be any real numbers. So you're going to see that in the case of the image, getting generators is going to be much simpler. Okay, you don't need that extra step with free unknowns and whatnot. You get your generators right away. So this is the typical vector, in other words. This is the typical vector in the image. And all you need to do is separate the unknowns. However, as you're going to see, more often here you will be getting generators that are not linearly independent. And you will need, so what do you do in such cases? You choose fewer of them. And this is a pretty tricky process. However, we're going to develop tools that are going to make it as simple as anything. So this will be X, 2, 1, 0, plus Y, negative 1, 0, 1. And here are your two generators. And guess what? They're linearly independent. Why are they linearly independent? Anybody tell me why these two vectors are linearly independent? Yeah, it's image, IMT, image of T. Yeah.
They have zeros where the other one doesn't.
Right. When I say generators, I mean vectors that span the subspace. So generators of a subspace when I say generators of a subspace, I mean vectors that span the subspace. What about 1, 1, 1? I'm not sure. I'm not following. So they're linearly independent because they have zeros at different. There are two of them, and they have zeros at two different places. So they're linearly independent and span the space. So it's okay. No worries. So so the dimension of image T is 2. Questions, please. Yeah, if it goes 2, 1, 0 and negative 1, 1, 0, please make sure you ask those questions. You send the message to everyone. So somebody's asking, what if they didn't have zeros in other in the same in different places? And the answer is you would have had to go with the longer method of taking x times the one vector plus y times the other vector plus possibly z times the other vector, set it equal to 0, 0, 0, and see if that equation is possible for anything other than 0. Okay, you would have to do it this way. There was another equation. There was another question. Because they are linearly independent, they span the subspace? No, absolutely not. The two properties generically are independent of each other. It's a little sensitive to be using the word independent here, but what I mean is that one is, if one holds, the other does not hold. We justified both of them separately. How? Since we wrote the generic vector on the image as a linear combination of these two vectors, we have automatically that those two vectors generate the subspace. So we have generation. Now, we said also that they're linearly independent because they have zeros at different places, and there are two of them. So this way we established linear independence. So the two properties in this case had to be established independently of each other. Okay. Let's do one more example. So this is going to be a little more interesting example. Let's see if we can handle it correctly. So find a basis for the image of T from R3 to R2 with a T of XYZ is equal to x plus y minus z, x plus 3z. Let me give you a couple of minutes to think about it, and then we'll do it together. Okay? Think about it. There's something a little more interesting about this particular problem. Okay, let's do it together now. So finding generators here is very easy. So you just, let's write down the image T as a subspace. So it's all the x plus y minus z, comma x plus 3z for x, y, and z belonging to R. Okay, so this is your generic vector in the image. So you take this and you separate your unknowns first, your variables, sorry. Okay, like so. And you get x 1 0 plus y, I'm sorry, 1 1, y 1 0 plus z times negative 1 comma 3. So these three vectors are automatically generators. This, and that. So they generate. Are they linearly independent? Now comes the question, are they linearly independent? And the answer is a definite no. You never have more linearly independent vectors than the dimension. Okay, so let's write this as a principle from now on. In a vector space of dimension n, n plus 1, n plus 1 or more vectors are linearly dependent. So anybody who gives you 3 vectors in R2, I don't care what those vectors are. I don't need to see them. If you have 3 vectors in R2, they have to be linearly dependent, which means we don't need all 3 generators. So we just need to choose 2 of them. Now, is it for certain that they have to be 2 of them? No, even that is not guaranteed. But you can easily see now that this one and this one are linearly dependent. So the 3 of them are linearly dependent. The 2 of them are linearly independent. So the basis consists of the vectors 1, 1 and 1, 0, which means that the image T has dimension 2. Since it has dimension 2, it's the whole R2. So image T is all of R2. I'm sorry, which part do you want me to explain again? Sorry, I missed what you want me to explain again. The remark in black? Yeah. So basically what I'm saying is that if you have a 4-dimensional space, let's see it in terms of examples. If you know that you have a 4-dimensional space, any 5 vectors in that 4-dimensional space or more, any 5, any 6, any 7 vectors have to be linearly dependent. Okay, have to be linearly dependent. I know that the dimension is 2 because these are 3 generators. They are linearly dependent. And I just found 1 less that are linearly independent. They automatically generate the space. Okay. Why? Because for many reasons. One of which is that they form a basis of R2. They form a basis of R2, which means that this third vector is a linear combination of the other 2. Okay, but you will see that in general, whenever you have a basis, all you need to do is find a maximum number of linearly independent vectors among the generators. No. It's not always like that. If you have 4 generators, the dimension could be 4 or 3 or 2 or 1. The dimension will always be less than or equal to the number of generators, but it depends on the situation. But the general remark that applies is the following. Here's the general remark that applies. If we have generators for a subspace, or a space for that matter, it doesn't matter, a subspace, then the largest possible number of linearly independent ones will form a basis. So if you have 3 generators, you always work backwards, starting with the number 3. You say, are the 3 generators linearly independent? If the answer is yes, then they form a basis and you're done. If the answer is no, then you check to see if among the 3 generators, there are 2 of them that are linearly independent. You can check all possible combinations. If the answer is no, again, they're linearly dependent, then you check 1, and so on. As you're going to see later, we're going to have a much better way, a much more efficient way. You're absolutely right. I could, there's the question of, I chose 1, 1 and 1, 0. Could I have chosen 1, 0, negative 1, 3? Absolutely. Could I have chosen 1, 1 and negative 1, 3? Absolutely. Because any combination of 2 of them are linearly independent. Unfortunately, we have run out of time. So I would suggest that you redo these examples several times based on the recording. And also, if you want more examples, you can come to my office hours. Okay? Let's take attendance though. And let's give as keyword the word kernel. You have 30 seconds to send me the word kernel. 30 seconds. Okay, in my okay, great. Any more questions, please? Any more questions? For your homework, I'm looking at your homework right now. For there's always a quiz. There's always a quiz. So the answer is constantly no. The one exception will be the day after the midterm exam. That's the only day when you will not have a quiz, or till we complete 15 quizzes. We're going to take 15 quizzes. So I'm looking at the homework for next time. The topic on the quiz will be one of the 2 things that we just solved. So either you will be asked to find the basis of a kernel or the basis of a of an image. Okay, so the first one, the first problem asks you to find a basis, asks you to find a matrix. So it's like what we did last time. The second one asks you for finding quant. This is too late. Okay, we said 30
Sorry,
seconds.
I was in the bathroom just now. I'm so sorry.
I understand, and it can happen occasionally. And that's why it's not a problem if it happens once or twice. Okay, that's, I mean, you know, if you're consistent, yeah, of course it can happen occasionally, right? Same thing to you, Matthews. Your attendance doesn't count. Okay, it has to be within 30 seconds of when I give you the keyword. And the second question is to find a the kernel. Tony, I just said the keyword has to be sent within 30 seconds. Otherwise, don't bother to send it. Okay, it doesn't count at this point. Okay, okay. So the second question has the kernel of a linear map, which is like what we just solved, the first type of problem. And the last question is the image of a linear map. You will see that in both cases, the linear maps that I'm giving you are very, very simple. And you shouldn't have any problem solving these two problems. Okay, but we can solve a couple of these examples next time, and you will see that finding the image of the kernel, I'm sorry, the basis for the image in the kernel is something that will be with us for the rest of the semester. Okay, so that's all I have for you today. I remind you that my office hours are in 10 minutes. And no, I don't think there will be another example before the quiz. That's why I'm putting this in a recording. These examples are as good as any example that we can do. It's more important to do an example by yourselves several times rather than see 10 examples by other people. Okay, so the quiz topic once more will be to find the basis either of a kernel or of the image of a linear map. So something like the two examples that we did. Okay. For any other questions, you can see me during my office hours. I have set the rules for attendance, and I'm not going to discuss them right now. My apologies. Okay. See you on